Okay, we had requests for a few types of questions through the communications portal, and one was a complete the square question, which I've got here in this first example. Second example asked for was an equation dealing with a radical. We've got a square root equals an x plus 1. And then something that uses the quadratic structure um, with a non-quadratic equation. So we'll talk about that. And then an equation that contains some rational expressions. So we'll do these four examples, and hopefully that'll help some people out. The complete the square process is nothing more than the quadratic formula. All you're doing when you do complete the square is you're mechanically doing the quadratic formula. And the first step in the process that we identified was to force the a value to be 1. So you divide all your terms by 2 in this case, because a is a 2. And by doing that, the a becomes a 1. And what that's going to set you up for is that when you factor, it's going to make your first terms in your two sets of parentheses be very easy. They're going to be 1x, 1x. So that's why we do that. Then, of course, the b now becomes a 4x. Okay? And the c value of the constant becomes 3 halves. Now, the second step of the complete the square process says to remove the constant to the 0 side. So this 3 halves is going to leave the left member and be put in the right member as a negative 3 halves. We use the additive inverse to do that. And notice how we leave a hole where that constant term was. That's because we're going to be filling that in. Now from here, the new b value, which happens to be a 4, we're going to split that in two and load that into the two secondary locations on each of the binomials. And so we're going to have a plus 2 and a plus 2. And in doing that, of course, we know we're going to get the x squared, as we already mentioned. And then on the outer pair and the inner pair, we're going to get 2x and 2x. So that's going to produce our 4x, just the way we want it. But as a matter of fact, by introducing those two split b terms in there, you're also going to cause a last term when you multiply the two binomials to be formed that isn't there right now. And that's why we left that hole. There would be, when you multiply those two binomials, x plus 2 times itself, there would be a factor of plus 4 in there. Now, adding that onto the left member, you have to also add that onto the right member of the equation, right? And from there, if we look at minus 3 halves plus 4, in order to add those two numbers, we're going to need a common denominator. So the 3 halves, denominator 2, and of course the 4 is 4 over 1. We're going to change the 4 so that we write it as 8 over 2. So we just multiplied top and bottom of that 4 over 1 by a 2. And now we can add these. You keep the denominator of 2, and the numerators get added, and that produces a 5. Now we have, it's noteworthy, we have seen a lot of mistakes in terms of people forgetting to add the constant, uh, the multiplied split b value to both sides. And then the other error we've been seeing is that people don't get a common denominator when they add those two values. So you want to be watching for that. Then we write this as a square. So we've got x plus 2 times itself equals 5 halves. And now to solve the squared equation, we do a square root to both sides. And in doing that square root, on the left-hand side, and I'll write it over here, we get x plus 2. So I'm going from here over here, equals plus or minus square root of 5 halves. And then finally from there, we remove the constant the left member. Put it in front of the plus minus. And remember that indicates two answers. -2 minus square root of 5 over square root of 2 and -2 plus square root of 5 over square root of 2. Now I also split up that square root into a numerator and denominator, and I did that so that if you want to have a rational denominator, you could use the rationalizing trick of multiplying top and bottom of that piece by square root of 2. And so you might write this answer like this. And of course, the other answer correspondingly becomes -2 plus rad 10 over 2, just so you have a rational denominator. One more time, you enter those into WebAssign by in the answer space, writing in those two answers and separating them by a comma, right? Because you have two answers there. And you don't put an x equals with it or anything like that. You just would put these two answers in, separated by a comma. So that's an example of the complete the squared process. As we move down to this second example on radical equations, the thing with the radical equations that we've noticed is people are not rejecting the extraneous root that can often happen when you're dealing with a radical. Okay, so as you look this problem over, step one in the process of solving a radical equation is to isolate the radical, in this case the square root. And so to get rid of that square root, we'll square both sides. Now that means we're multiplying square root of 1 minus 3x times square root 1 minus 3x, right? Squaring the square root. And we're also multiplying x plus 1 times itself. So it's x plus 1 times x plus 1. On the left should be really apparent that we're going to get 1 minus 3x. Okay. And on the right hand side, if you need to write it all out, what you're going to end up with is x squared plus 2x plus 1. And now we see the x squared and we see the x, so we think get one side to 0. So I'm going to move the 1 and the minus 3x from the left member to the right member. And in doing that, I get x squared plus 5x. And the constant 1, when subtracted from the constant 1 in the right hand member, goes away. Now, from here, pretty easy equation to solve. If we just factor this into x times x plus 5 equals 0. And then we split those into two cases, either x equals 0 or x plus 5 equals 0. We get two answers. Of course, our x equals 0 and our x equals minus 5. And what we've been seeing from a lot of people is people plugging in both of those answers. Well, before you do, you should check to make sure they both work. Now, you need to check in the original equation that you were given. You can't check it in anything that you created during the process. So you go right back to square root 1 minus 3x equals x plus 1. And then if we replace x by 0, we get 1 minus 3 times 0 equals 0 plus 1. So we get 1 equals 1. And so that answer checks. The 0 answer is a keeper. And now we'll check the other answer. Again, using the original given equation. And we're just going to replace the variable by the other answer that we came up with, which was minus 5. And with minus 5 as an answer, on the right hand side we get minus 4. And on the left hand side we get 1 minus 3 times minus 5, which gives us 1 plus 15, which gives us square root of 16, which is the square root of 16 is just a 4. There's no plus or minus in front of that. That's just the principal square root. So it's just the positive 4. And does 4 equal negative 4? That's a no. So the negative 5 answer that came out of our solution has to be rejected. It's not a legitimate answer. Okay, it's what we call an extraneous root. It's an answer that's caused by the method of solution. And so especially with radical equations, you want to check your answers to make sure they're right. So the only answer that would have gone in the answer space is the answer 0. And if you put in 0, comma, negative 5, it's going to be marked wrong because one of your answers isn't correct. So that's an example of the radical equations. People seem to be doing them pretty well, but the biggest error is people not rejecting extraneous roots. So you want to watch for that. Example number 3 is an example where we talk about form and structure. And the equation number 3 is identical in form to a very elementary algebra type equation that you see all the time in the high school mathematics. It looks like this: x squared plus x minus 20 equals 0. The exponents are a ratio of 2 to 1, and you would easily factor this, right? To an x and an x and a plus 5 and a minus 4. Continue as such. Well, the fact that you have that same ratio between your exponents here makes this an easy situation to factor. All we have to do is identify it as an x squared and an x squared in our two first locations, because x squared times x squared will give you x to the fourth. And then the factors of 20, 1 and 20, and 2 and 10, and 4 and 5 are your integer factors. And pretty apparent, we're going to use the 4, 5 pair. And we want a plus 5 and a minus 4, as the signs are different. And we want to end up with a plus 1x on our b term. And so that's how that factors. Now from there, we use the same idea we used in elementary algebra. You set each one of those factors equal to 0. And in doing that, we have a little more work to do over here. X squared minus 4 should be recognizable as difference of two squares. So we're going to factor those into a conjugate pair of x plus 2 times x minus 2. And then each of those factors gets split and equal to 0. So we got one answer of x equals minus 2. And out of this factor, we get an answer of x equals 2. And those will check. Now, the other factor, the x squared plus 5 equals 0, that gives us x squared equals negative 5. So when you do your square root and you get plus or minus square root negative 5, well, the problem is this is an imaginary answer. And you're working over the real numbers. And so perhaps the instruction should have been changed to say solve for all real values. Right in here, we should have maybe put in the word real. You're only looking for real solutions, and in the calculus, you'll be doing the calculus of the real variable. So answers like this get rejected because they're not real. They're imagined. A square root of a negative number can't happen. You can have a cube root of a negative number, but you can't have even roots of negative arguments, negative numbers. So that answer gets rejected, and the only two acceptable answers would be minus 2 and 2. Right? And on that question, we have seen a few people trying to include the imaginary answer. So that's not really on you. That's more the way we described the question. We should have made it more apparent that you're only working with real numbers. So, in the future, if you get an answer that's imaginary, reject it. Don't include it in your solution set. And then our last question here is an example of an equation that contains rational expressions. And So what we've got here is 3 over y minus 2 plus y over 2 minus y. And it helps a little bit in this example to notice something about these two denominators right here. Right? Normally when you have denominators and you're adding or subtracting, you want to get a common denominator. And in this case, it's very easy to get a common denominator if you notice that they're negatives of each other. This y is a positive y, this y is a negative y. This 2 is negative, this 2 is positive. Those two denominators are signed opposites of one another. Okay, so to get a common denominator of, say, y minus 2, okay, I would have to do nothing to my first fraction. And the second fraction, I would just multiply by negative 1 over negative 1. And so that would give me as a numerator now, in the combined fraction, 3 minus y equals 5, or if you want to call it 5 over 1, because that's usually the technique with rational expression equations, is to create a proportion and then cross multiply. You create that proportion by getting a common denominator, sometimes using the product of the two denominators, but in this case it was a little bit easier because the denominators were signed opposites. So now at this point, if I do the product of my means and the product of the extremes, I get a new equation. I get 3 minus y equals 5y minus 10. Okay? And then from there, if I bring the y over, I get 6y. And if I bring the 10 this way, I get 13. And then dividing both sides by 6, I get an answer of 13/6. Now, anytime you're working with rational expressions, and if the rational expression has a denominator with a variable, you want to be careful. Um, and so back at the very beginning, it's noteworthy that y cannot be 2. Okay, if when I did this solution, if I would have ended up with an answer of y equals 2, then I would have rejected that solution, right? So just backing it up, suppose this 3 right here. Suppose that 3 would have been a 2. It wouldn't have changed anything. The equation would have ended up looking like this. Then when you cross multiply, you'd get 5y minus 10 equals 2 minus y. Same way, bring the y over, get the 6y. Bring the 10 this way, add it, get 12. And divide by 6, you get y equals 2 for an answer. And you think everything is good, and in your answer space you put a 2, it would get marked wrong. Because if y is 2, 2 minus 2 in your denominator is a division by 0. So on any of these questions, when you get an answer, you want to do a double take on it and make sure that it's okay. Now, as it was, this was a 3, and we solved it and got 13/6. So 3 over y minus 2 with a 13/6 in there isn't going to cause any problem. And of course, the other denominator is just the signed opposite, so that isn't going to make any problem. So hopefully these videos people asked for are helpful, and you can take a look at Unit Test 4 and see how you do with that.